PPA-CF is the strongest filament type I can print, and this one is from Sunlu. I already did few testings, extremely strong material, but it looks like we will not be able to buy this filament. Hello, welcome to another filament testing video. Sunlu sent me several technical filaments for the testing, including this one, PPA-CF in black color. I got all these spools for free, but there is no additional payment from their side. But this video and the whole channel is sponsored by Polymaker and by my Patreon supporters. Now this filament is so new that currently when I'm recording this intro, there is absolutely no information on their website. I don't even know the price, but if I will get it, you can see it here. I will just mention a few overall properties of the PPA-CF according to my experience. Polyfilamide reinforced with carbon fibers is the strongest filament type I can print on my printers. It has a great temperature resistance, high stiffness, low creeping, which is a typical weak point of the nylons, and this is less sensitive to moisture even compared to the PA12, but more sensitive compared to the PPS filaments. On the box there is no information what is inside. This is written by me. Nice vacuum packaging, and this material is good against the moisture, and I just double check that it is not a resealable bag. And finally on the sticker I have some print informations. Print temperature between 280 and 300 degrees Celsius, bed between 90 and 100, and spool temperature resistance up to 110 degrees Celsius. This is important for the drying. Probably it is made from the polycarbonate. On spool the sticker with same information I already mentioned, and I like this kind of the spools with the holes. This is important for the drying, and temperature resistance I already mentioned up to 110 degrees Celsius. End of the filament was glued. Let's see how brittle is the filament itself. Oh, okay, brittle, so it has to be measured. Start angle 30 degrees. Around 70, so this is quite brittle filament. And the printing I will do on H2D and not on H2S because it handles better these brittle filaments. Oh, it explodes. This is H2D and the filament is loaded into left extruder. Let's see how much moisture it has in it. I will extrude a little bit some filament. Oh, I think it has to be dried. See this? It stopped with the extruding, but it is still oozing. It started, this is now the second layer. Everything is fine so far, but probably I can experience some over extrusion, but I'll measure them later. And also I'm curious about the bed adhesion with this texture PI sheet without any glue on it. Let's check the purge line. On the edge acceptable, but probably I'll switch to the generic plate with my main test objects. Bed adhesion check. Definitely I will use a glue with my main test objects. Let's measure them quickly. 20.1. 100.03. I did a calculation. It is explained in one of my earlier videos, and in this case this C constant offset is more important, and if it is closer to the zero it is dry filament, and in this case we can see this is a relatively low number, so theoretically according to this filament should be dried, but let's measure it with that drying measuring method. Before the drying I am measuring the weight. This is in grams. After measuring, it goes to the Sovol SH03 filament dryer. The maximum temperature for this dryer is 85 degrees Celsius. And this is one of the measurings every 1 hour. And this is the last measuring. And it looks like there is no big changes anymore, and I can analyze the data, but also can start the printing. These are measured values, and on this graph you can see the mass in function of time. And if I could calculate somehow what is the value in infinity, Here it became a constant, and from that I could calculate the start moisture. And actually I made a tool for this. I have to copy these numbers. It's in others, drying tool, and here I have to copy the numbers, interval 1 hours, calculate. And it will place this graph on the points, but it will do all the calculation for us. The most important is this dry, and for this we can calculate the start moisture. Actually it is already calculated, and in this case it is quite low, 0.36% approximately. So actually it was quite dry at the beginning too. Only I'm not sure why that oozing appeared. Again I am checking the oozing, and I can see that the oozing is still here. It is reduced a little bit, but it still appears, so looks like here we have the oozing even with relatively dry filament. And again reprinting those objects for the measuring. Engineering plate with the glue, the adhesion is great. And now let's measure these test objects. Now there is no stringing, for example, like you can see here. .07 100. And this calculation is finished too. Absolutely no changes on the scale factor, exactly the same value, but what is more important is the C constant offset, and in this case we can see that we could reduce it with this drying. It is much closer to the 0 now, but even this was quite dry, so I'm not sure why that oozing appeared, but now definitely it is dry and ready for the test objects. Settings in the slicer. Generic PPA-CF is the start profile. Chamber temperature 60 degrees Celsius, 300 degrees Celsius. On the nozzle I raised this a little bit. 6.5 is the maximal flow. And the part cooling, I find these 2 seconds a little bit low, so I increase this to 4 seconds per layer. Printing time will be approximately 2 hours. Here you can see a few seconds of the printing. Completely straight parts without any warping. Actually we hit the chamber and carbon fibers really helps here. The adhesion to this engineering plate is great. And I'm printing a few other test objects. This French you already saw in my earlier video. And the handler is a great application for this strong filament. Let's start the mechanical testing. Tensile test with horizontally printed objects. Again, for the better reference, I will include the data for the average PPA, which I calculated from 9 pieces from that summary table, and only one don't have fibers. And we can see that the tensile strength is extremely similar, but in both cases this is very strong compared to any other filament type. Layer adhesion, vertical test specimens. Compared to the average PPA, this filament is weaker by approximately 30%. But look at this table. This is my rating for this size of the test object, and even this is actually great layer adhesion. Only compared to the average PPA or compared to the horizontal object, it looks weak. Shear test, and I'm starting with the vertically printed ones. And for the horizontal shear test, I'm switching to stronger equipment because I know that 200 kilograms is not enough. Printed in horizontal position, with all PPA filaments I had to switch to that stronger equipment because 200 kilograms are not enough. And yes, in this case the average PPA is stronger, but the difference is negligible, I think. And similar with the vertically printed test objects, and in both cases these are extremely strong compared to any other filament type. Torsion test, and I'm starting with horizontal printed objects. 2.1, 2.2. And now vertical with the same dimensions. 1.3. Printed in horizontal position, load and 90-degree rotation, a little bit below average PPA. Only printed in vertical position. Here we can see some bigger difference. I'm not sure what happened. If the filament wouldn't be discontinued, I would reprint this and I would recheck, but in this case I just don't want to invest more energy into this. Impact test, and I'm starting with the Sharpie hammer. You can see 3 measurings in right upper corner. And now switching to the ISO standard. ISO the first test. and measured numbers again in the right upper corner. Overall, PPA-CF is quite a brittle material, and this filament is a little bit weaker compared to the average PPA. But still, this is, let's say, 2 times tougher compared to the average PETG. Just few words about my temperature test. Fiber reinforced PPA never started with deformation in my test and always reached the maximal temperature of my equipment. There is only one exception with one filament, no fiber reinforced PPA. Additionally, annealing can increase this heat deflection temperature, but unfortunately I'm not able to measure this with my current equipment. Grip tests the deformation under constant load, and I have several tests in the progress: PPA-CF, PC acrylic and PPS filament. The load is 1.25 kilograms. The gap is too small for the bolt, so I have to go around. 12.49. It's the last 5th day of the measuring. 12.66. Removing the load. On this graph we can see the distance between two reference surfaces, and we can see very small deformation on the Sunlu PPA-CF even compared to the average PPA. But the creeping is the difference between 2 days, and that's what we can see on the second graph. And we can see this is extremely minimal, even some negative values here, because probably this is inaccuracy in the measuring, and slightly better compared to the average PPA. 3-point bending test. Distance between supports is 50 millimeters, and I'm placing these loads and measuring the deformation after 1, 30 and 60 seconds. This is under 5 kilograms, 10, very minimal deformation, and basically no changes during this 1 minute. Every PPA filament is very good in this test, and look at this PPA-CF, significantly smaller deformation, extremely similar to the Bambole PPA-CF, which is, already checked my summary table, the stiffest material I ever tested, and this one is extremely similar. Our results one more time: creep test, tensile and layer adhesion, shear test horizontal and vertical, bending deformation after 30 seconds, bending deformation after 1, 30 and 60 seconds, torsion test, temperature and impact test. When I need some really strong part, which resists to the bending in XY direction with the high tensile strength, low creeping, I use PPA-CF. There is one bigger disadvantage of this material, except being a brittle, that's the price. PET-CF, let's say, it would be some budget-friendly option, but I could see a lot of similarities of this Sunlu PPA-CF compared to the Bambole version, but this should be significantly cheaper. And when I almost finished the video, I asked Sunlu to confirm the price because I couldn't find it on the internet, and only then they informed me that sorry, but the filament is cancelled. And I wasn't sure what to do, so that's why I started a poll on my YouTube channel, and almost 90% of you voted that you still want to see the video. I'm not really sure about the reason for the cancellation, but I have the feeling that one of the main reasons is that the filament itself is very brittle. The fact it is brittle and it may break in some stock printers without modification, like I don't know, Bambole H2S, GDQ2, Creality K2 Max, these are which I tested. But actually I'm able to measure this, and I could measure that other brands have similar brittleness, like Bambole PPA-CF for example. But it looks like for the Sunlu it's easier to cancel the filament than to deal with the customers and their problems. I'm not sure, I'm just guessing, maybe there are some other reasons too, but the fact is that this is really strong filament. Okay, so this was my experience with this filament, so if you have some other, I don't know, with PPA, then fill us out in the comment section. Huge thanks to Polymaker for sponsoring my channel, and to all my Patreon supporters and to their donations, because they keep me motivated to do this kind of less popular videos too. Thank you for watching this video until the end, and happy printing!